Okay. I'm just going to talk about this very briefly. It's very kind of not that important at all. It's not polynomial at all. It's just that I wanted to talk about POM-DPs. I don't really know what a POM-DP is. It's a partially observable Markov decision process. And the thing I'm going to write on the board is not exactly one of those that I know of, but it's close. Okay. So what I wanted to say is just that there's a monoid where it does what's called discounted reward when you add. So in discounted reward, you say if I have a bunch of numbers, R1, R2, R3, R4, or whatever, and I get R1 now, R1 a while in the past, R2 a little bit less in the past, R3 just a minute ago, and R4 right now. I want to discount old rewards, like rewards you got in the past are worth less to you than current rewards. And so what they'll do is they'll do like some discount factor gamma cubed for R1 and gamma squared for R2 and gamma for R3. And this way, like more recent rewards are more salient or more important. And that always felt to me like, oh man, it's some new thing, but it's just a monoid. So there's a monoid for discounted rewards, and this is completely irrelevant to poly. It's just that I wanted to talk about POM-DPs. And so the way it works is if you have any rig, which means a ring without, like you don't need negatives. So if you have natural numbers or non-negative reals, any rig, some people call it a semi-ring, and you pick a gamma in it, that's your discount factor, then there's a new monoid where you kind of keep track of how long ago you got keep track of how long you have something for, and then a number, and you add using this plus thing. So like n1 r1 plus over gamma n2 r2, the amount of time you've had it is n1 plus n2, but you discount your r1 because you just like waited n2 minutes. So whatever r1 was, you discount by gamma to the power n2, gamma times gamma times gamma, n2 times plus r2. And the reason this works, 1 second, is just, or this gives you this, is like if everyone's taking 1 second to go, you really do get the thing that you're expecting. Yeah.
That's cool, but what if you don't want squaring? What if you don't want another function from gamma to gamma?
So what if you don't?
I guess that's defined by.
What if you don't want what? Oh, gamma. Well, yeah, once you have times,
yeah.
Then gamma to the power n just means gamma times gamma.
Yeah.
But I think we said
Yeah.
Your choice of
Decay.
of times is what determines
Yeah,
what's
you're
happening to gamma.
yeah,
If
yeah,
you
yeah.
wanted to choose something else, like if you wanted to go down instead of
Yeah, you could pick max plus. You could pick any rig you want, and you'll get this sort of thing. Yeah. Okay, now the thing I want to talk about next is kind of like close to POM-DPs, or these are called partially observable Markov decision processes, and I'm not going to define them exactly because I want something that's as workable as possible and not necessarily the definition in Wikipedia, which may or may not be the most workable thing. I don't get the sense that they picked it because it's a monad or something, whereas the thing I want to pick is like almost exactly the same, but it's a monad, so it's, I don't know if it's the same or not, but I know it's like has good properties I like. Okay, so the idea is, I just want to like, I got the sense that everything was getting very abstract, so I wanted to give like a more down-to-earth or a machine-y type thing. And so let's talk about coalgebras. But now we have trie. So wait, which way does it go? Okay. Okay, suppose, yeah, so what does a machine like this do? It's like a huge thing to write, but what does it mean? It's a state machine, or it's a Moore machine. You know, it's some machine. And for every state, it picks a lottery. So maybe it says 25%, 50%, 25% for 3 different tickets or something. So every state gets sent to a lottery. A lottery, if you remember, is like a natural number. Soon we're going to talk about monads, and lot is a monad. But what is the carrier of this monad? You pick a number of tickets. You pick a probability distribution on those tickets. And then someone returns to you one of the tickets. Okay, so every state goes to a lottery, and given a ticket, so you don't know, you get this lottery, but then once somebody picks a ticket, you get to see an output. Without lot there, you would just for every state get an output. But now you get a lottery on outputs. I'm going to erase this line. For every state, you get a lottery where for any ticket that's chosen, out comes an output. And then given an input, instead of just getting a state deterministically, that input that you got gives a lottery. And given a ticket of that, you get a reward and a new state. So it says, for each state, S, a lottery, and for each ticket, an output. Let's see, a lottery NP, N of S, P of S, I guess. And for each ticket, N in NP, NS, an output, B. I'm not carrying, I have like all this subscripting I should probably be carrying along with me, but maybe you just can read it anyway. For each state, a lottery, and for each ticket in that lottery, an output, and for each input, A and A, a lottery, N, A, P, A, or something. And some number of tickets and a probability distribution on them, and a reward, M in M, and a new state. Now, so you've got the state machine.
What's the motive for this?
The motive for this, yeah, there's lots of different ones that you might be interested in. So let's see. We have sy to the s to by to the a. For every state, you get an output. For every input, you update your state. For every state, you get a distribution on outputs. I'm in some state, and I'm doing something, but I accidentally like twitched. Oops, that wasn't part of my state. Or like you don't see my state exactly. You see a lottery on my state. You don't see my state. Some other thing in the world is running a lottery. We spent a lot of time on this after class the other day to like construct like the universal, what seemed to be like the universal lottery winning ticket picker. In this thing, for every state you get a lottery, and for every ticket of it you get an output. And then given an input, you get an updated state. Or you could say, for every state, I get to see my output for sure. I get an actually observable state. But given an input, I just get a lottery on next states. I get a lottery, like 50%, 25%, 25%, and then given a ticket, I get an updated state.
Say that last one again.
For every state, I get an output.
Yeah.
Then given an input, I don't know my state. Given an input, I get a lottery,
Yeah.
like 50, 25, 25. And then whatever ticket is chosen, that gives me a state.
How come
Yeah.
going that direction, it bypasses the mapping to the directions of the first term in the try, like to A?
In this one,
Yeah,
given a state, I get an output.
right,
And for every input, I get a lottery.
right.
And for every ticket, a state.
I mean,
Oh, maybe you can't read how. Oh, I haven't really talked through.
You're sort of,
I got confused about where the wiring was going for everything for that.
Maybe I need to talk. Okay,
so
I think,
this is sort of like
okay.
You're getting 4 steps here, right?
Yeah, and then the next one.
One step is now 4 steps that involve this composition.
So, okay, so the big, on the left, the big try thing is, you can decompose it into those 4 polymaps. Is that what you're saying?
Yeah, I forgot to go over how you get maps into a try. Sophie, is that what you're going to say? Or something else?
Yeah, I was also confused about something you said, but maybe it'll.
Let's do that. What were you confused about?
You said something you don't know your state, but I thought you got to use your state.
In this one?
Yeah.
In this one, given a state,
Yep.
I get an output.
Yep.
And for every input, I get a lottery on states.
Yeah.
Yeah.
But that lottery can involve the state I can.
The lottery definitely involves the state you started in, but it has some, distribution on next states, yeah. So to tell you why I can read things the way I am, I have to tell you how to map into a try, and I haven't told you that yet, so I'll do that next, yeah.
A small question. You probably said it earlier, but is try associative?
No, yes, try is associative. All monoidal structures are associative, but it's not symmetric,
But not, okay, right,
yeah.
I mean, maybe polyboxes would help.
Oh, yeah, polyboxes would help. Okay. So a map from P, yeah, yeah. Okay, so a map phi.
I don't really know how to read those.
Yeah. Oh, you don't know how to read those? These are positions. These are the directions above it. Like Joachim drew like these pictures like that.
Yeah.
These are the elements of B. These are the elements of the fiber over those things. These are the positions. These are the directions.
I think of it also like in like B, Y to the A.
Yeah.
Put a B in the bottom box, and then a bunch of A in the pier above.
Yeah. Well, yeah. B. This will be of type B. This will be of type A.
Yeah.
So here we have the thing in the bottom is going to be of type P of 1, so some kind of I, and this will be P bracket I, but we don't know what I someone's put in there yet.
Right.
So, yeah. Sure. Okay. So to give a map phi like this, you give a function. So let's suppose you have a little spreadsheet. You fill in that, and that, and that, and then the machine will fill in the other parts. So it looks like, phi looks like this. Okay, so phi says, whatever you stick in here, I will give you something in there. I have a formula for that. Once something appears here, then the directions open up.
When you say fill in, like it's like
For lambda I colon P of 1, phi 1 I.
yes, but like
Yeah.
what I mean is that phi. Once you have a phi,
Given a
calling
phi,
it, so to speak,
calling it,
is like corresponds to filling in the blue boxes.
no, calling it on the user filling in the blue boxes fills in the white boxes. The user fills in the blue boxes,
Yeah.
the formula fills in the white boxes.
Yes.
Phi is the formula.
Phi is the form. Yes.
Yeah.
Okay. Gotcha.
Okay. So somebody comes along and fills in an I.
So it's like a formula, but you have two or
It's a multi-step program.
things that has to be supplied.
It's a multi-step formula.
Yeah,
The decision, someone says, I need to pick a direction here, and they delegate it to this side.
Yeah.
Then what's going to happen is I is going to be sent to a position of Q1. It's going to be sent somewhere, and that's going to open up the directions there. You don't know what directions are because you don't know what position you're at yet.
Pick the menu item.
But now you picked you picked that. Now the directions open up, so
Yeah.
somebody fills in a direction. then the formula picks a thing here. Now these directions open up. So somebody picks a direction there, and the formula tells you what goes there.
Sometimes I get confused because, like, to give phi is also to choose a bunch of things.
Yes, it is to choose the arrows.
Yeah, but like this is what phi is established. So like,
Phi is,
in order to call phi, so to speak, you need to give 3 pieces of data.
yeah. In order to call phi, you fill in the blues.
Yeah.
But you can't fill them all in at once. You fill in this one. Phi tells you what the answer is here. That opens up your choices there. Yeah.
Right.
Okay, so let's see. So to give, what are polymaps from P to Q1 compose Q2? They are, for every I in P1, a choice of thing in this position there, right? But what is a position there? It's a choice of, it's a choice of J1 in Q1 of 1, and for all E1, I don't know, E1 in Q1 J1, a choice of, like, sorry, I'm kind of cheating. I'm kind of telling you what I want the answer to be instead of what it is. It will be isomorphic to this thing, but what it really is we would it's this really gross looking thing, but I'm just going to do it because I feel like I should do it for you. It's a position in this.
In that, yeah.
So a position in that is a J1, J2 in sum over J1 colon Q1 of 1 product over E1 in Q1 J1 of Q2 of 1. The gallery is sad, and they should be. So then product over,
Oh, it's still good. So
given a direction here, which is an E1 in Q1 of J1, and it's an E1, E2 in Q1 compose Q2 of bracket J1 comma J2 P bracket I. Okay, that's the whole formula, but it's terrible. So I'll tell you what it's isomorphic to, and this isomorphism is using just properties of sigmas and pi's. Okay, so it's isomorphic to something much easier. Okay, so anyone who is sad should realize that we're about to be happier. Okay, we're about to draw this picture.
Yes.
This thing, when you collapse it and pretend it's a single polynomial, looks really hard. I mean, it is, Q1 compose Q2 is a polynomial.
These composition things happen.
Yeah, Q1 compose Q2 is a polynomial, but it's got a lot of stuff going on in it.
Functions all over the place.
And we did, this is because someone took this thing and used the distributive law to collapse it into a polynomial. If they hadn't made themselves do that and they let themselves have sigma pi, sigma pi, sigma pi, everything would have been so much better. Okay, so let's just see what this is again. So it says for every position in P of 1, pick a position in Q1 of 1, and for every direction there, pick a position in Q2 of 1. And for every direction there, pick a position in P1, Pi. Pi, sigma pi, and this is really a sigma, right? Sigma of 1, yeah. Okay, so this thing is just saying, for anything you can fill in blue, tell me what to put in Q1 of 1. For anything you can fill in blue, tell me what to put in a Q2 of 1. For anything you can fill in blue, fill in the original, the top thing.
Sorry, what was it you said about being a sigma of 1? I didn't catch
Oh, A is sigma over A and A of 1.
that. Oh, okay.
So like if you wanted to, if you like nice symmetry things, you could put sum over D in Pi of 1. And you can always kind of end in a 1 if you want to. This one is like and stop.
Yeah.
Yeah.
In the big sigma thing, like the very big sigma.
In this very big sigma, yeah.
So what is J2? Like,
J2 is a function that takes any E1 and gives you a Q2. So J2 is of type product over E1 in Q1 of J1
The manuscript
Q2.
you write J bar, right?
Yeah, Nelson wanted to write J bar. Yeah.
What's J for what?
It's a
Like-
notation
J bar is
for
a function.
functionally dependent.
I like to write B as a map from A to, like B as the name of a notation for functions into B.
Yeah.
Or B is a pi over A and A of B, A. Yeah.
And J bar corresponds to.
I mean, it's just whether you would want to call this B or you think like, no, I really ought to call that B bar, that's a notational choice.
Oh, okay.
And sorry,
Okay.
what was it that you replaced with that sigma of 1? I hadn't written that down.
Which one?
Like the sigma of 1, what was that before?
Oh,
you,
it's this.
just A.
Yeah,
Or
and
just
therefore,
P of one, P bracket I.
Oh, just
P bracket I,
okay.
yeah.
Thank you.
Okay. Yeah, so mapping into a composite is easy. Mapping out of a composite is hard. There's no pretty polybox formula thing, no pretty polyboxes for mapping out of a composite, or at least I don't know them. Maybe you could come up with them if you're good at graphical notations. But there is nice, pretty polybox notation, and it's a conceptually easier somehow to map into a composite, into a trie. It's hard to map out of a trie. Mapping into a trie, everything kind of relaxes and unfolds, and everybody's happy. I don't know. This thing just kind of, so if you want to map from P into Q1, compose Q2, compose Q3, compose Q4, you just keep going. Yeah, you just go. Yeah.
That is cool.
It goes like that, and then that, and then that, and then that, and then that. P.
So, I know you just said that it doesn't work out nice, but could you just give us a visual indication of how bad it is to go the other way?
Go the other way?
Yeah. Like try to see
Yeah.
where would it break down?
Out of a
Show us
try.
where it blows up.
Yeah, to map, the question was if I tried to map from P1, compose P2 to Q, what would you have to do? Well, positions of this, a position of this is a choice of a thing here together with a map from here to here.
Yeah, so like you would have to take.
So this data goes there. And then given this, it goes there, and then this one will open up, and then it goes there. But remember, this thing is touching that arrow there.
Yeah.
So it's kind of like, I don't know what that
Maps
is.
like that are, you can do that though, right?
I mean,
Or can't, I mean.
yeah, there is such a thing as a map from P1 try P2 to Q. And in fact, when we talk about monads, we'll be doing, which is next, we'll be doing that a lot.
Okay.
It's just that there's no pretty pictures for it that I know of. But there are pretty pictures for mapping into a trie, into a composite. And that's because this sort of thing just works the whole way. A map from P to Q1 compose Q2 to compose 3Q compose Q4 is for every position of P, a position of Q1, and for every direction there, a position of Q2, and for every direction there, position of Q3, for every direction there, position of Q4, for every direction there, a direction of P.
See what you said to me, David, when I was confused it's like time. This is the metronome clicking.
Yeah, try is like time.
Yeah.
A former postdoc working here named Brandon Shapiro and I explained in a paper how like tensor is a three-dimensional space. So a monoidal product is one-dimensional kind of if it's not symmetric, it has no braiding. It's called two-dimensional if it has a braiding, and it's three-dimensional if it has a symmetric braiding, because like you can go around yeah. So tensor and trie are kind of like a 3+1 dimensional space-time, and we talked about Minkowski space and stuff like that. It was like that part of the analogy is not super compelling, but it works, and tensor is a lot like space, and trie is a lot like time. And I have no idea why you mentioned that just now, except that apparently I said it to you and it was helpful. But
Well,
somehow, yeah, this
the
kind of
dynamics,
ticks.
the
It kind of
notion
ticks forward.
I think maybe it's because it's in the manuscript that it's a way of doing multiple steps, defining
Yeah,
Discrete steps.
multiple discrete steps. Yeah,
multiple discrete steps,
Yep.
chaining them together and getting one step.
That's right.
Now that composition is now a discrete step.
Yeah. So the idea is that time we feel like is this real coefficient or something, or this real number ticking forward very fast, right? 2.6839 seconds ago. But in this point of view, it's discrete. But what it's really talking about is dependency.
Right, yeah.
It's about dependency.
Very
Yeah,
cool.
yeah. That something opens up because of something in the past. Like a future opens up. You can't know even the possibilities of the future are not there or disclosed until the position is taken. Yeah.
I thought there was one case that was very germane to this discussion where mapping out of a composite is routine and beautiful.
Yeah.
Which is if you have like a composite over on the left of two polynomials mapped to a composite on the right of two polynomials.
No.
Right? Like S
Well,
y to
yeah,
the
so-
S
so-
composed with S y to the S. to the
Okay.
S.
Yeah, it's true that for all monoidal products,
Yeah.
I usually like to write 1, 2 because it's time. So here it actually feels correct to like definitely use 1, 2 whenever I'm using a trie.
Yeah.
Okay, to Q1 compose Q2, there's tons of these that are ugly, but if I already had in hand, if I wanted one of these, it would be enough to get one of these and one of these.
Yeah.
If you had these two, you could get this one.
Wait, can you go the other way?
Yeah, sorry.
Yep.
Okay, let me talk about a notational thing, I guess. If I have like A and then I write B, it means that from A I can derive B. And that's very common in like logic. They'll like write a deduction rule with a line. And 2 lines means that from A you get a B and from B you get an A. That's type theory. I have started writing A question mark deduces B question mark, meaning that if I had a B, I would get an A. Because sometimes it's useful, like I tend to write on my paper what I want, and then I tend to say, oh, if I had this, I would have it. Oh, if I had this, I would have it. So I tend to like deduce what I need, and that deduction of need is opposite to deduction of have. So I don't know if that's okay, but this question mark thing, if I want one of these, it would be enough to have one of those and one of those. But given one of these, we cannot deduce those two. And so Nate, what I think you were talking about is if I had a map from P1 to Q1,
Yeah.
yeah. and I had a map from P2 to Q2,
That's right.
then I would be able to
That's right.
I would be able to get a map from the stack to the stack. Yeah.
And where a particularly delightful case is over on the left, you have S y to the S, right?
Yeah. So it sounds like you're trying to talk about comonoids, which is mainly what tomorrow's all about.
Yeah, it was just that seemed germane for. what
Yeah,
you
that's
said
a
earlier.
very good point. So, and the reason that works is that trie is a monoidal product. And so if you have a map from P1 to Q1 and P2 to Q2, then you do get a map from P1 trie P2 to Q1 trie Q2.
And you're saying that's true for any monoidal.
For any monoidal product, every monoidal product works not only on objects, but also on morphisms.
David, can you say again the stuff about dimensions? is one-dimensional, or because it's fine to be very loose about it.
Yeah, monoidal products that are like, I have these two things, A and then B or something. Well, I can't reverse the order, otherwise it's not the same thing. There's something called a braiding that says that I have a map from A tensor B to B tensor A. And the picture of this is kind of like they go around, and if you do it twice, you get back where you started. It's an isomorphism. But it's not the identity. Or sorry, what? Wait, what? I'm confused. Sorry. It's an isomorphism, but it's not the case that if you go around twice, you get back where you started. Symmetry is that if you go back and forth, you get back where you started. Okay. And so that works when there's a three-dimensional thing, and sorry, I'm blanking here, but like if you have 3 dimensions, then when you go around, you can kind of like go like that and untwist it. Yeah. Okay. Okay. So I wanted to talk about I wanted to talk about this. This was the point of all this stuff. Was that I was reading through this and I could tell that you weren't following. I think I could tell you weren't following. So let me go through this again. Given this kind of crazy situation, maybe we shouldn't pick such a crazy one. Or we could. Yeah. Okay, let's do it. It's just reading. So given a state, for each state, a lottery. And for each ticket, an output. And for each input, a lottery, such that for each ticket, I get a reward and a new state.
So could I copy that down even as you say it?
Yeah.
So
It's written here.
okay, thank you.
For each state, so I'm just going through one of these except with 4 things.
Yeah.
For each state, a choice of lottery, and for each ticket, an output in B, and for each input, a lottery,
Yeah.
and for each ticket, a reward in my monoid of rewards, M, and for each of unit type, a new state.
And where's the distribution occurring?
Y distribution.
Oh, okay, I'm sorry, I'm thinking of the,
Lottery?
no, yeah, sorry, I'm thinking about the other case where the collectives case, which is different, where you're dividing up all the
Oh, yeah.
the gains.
Yeah.
Okay, thank you.
A mini exercise, oh, sorry.
Say again?
I said a mini exercise could be, can people figure out what sy to the s to by to the a try list is?
Okay, yeah, let's try that. A little exercise, sy to the s to by to the a try list.
So one thing I'm still missing from the board number 8 there is what are those 4 maps, those 4 polymaps, like how do they relate?
These 4 things?
Yeah.
In the top one, you have a deterministic system. For every state, you get an output,
Okay.
and for every input, you get a new state. This is called a Moore machine.
Yeah.
Here, for every state, you don't know what you're going to get as your output. You have a distribution on outputs.
So you're just trying to build it conceptually by breaking it apart?
I'm just saying there's 4 different ways that you can have a non-deterministic automaton. In one of them, it's deterministic. It's trivially non-deterministic. It's deterministic. Okay. The next one, given a state, you get an output non-deterministically, which also gives you a way to take an input and get a new state. And given an input, you get a new state. It's still allowed to be based on the lottery ticket that was chosen.
So
But the same lottery ticket that was chosen determines how the output is chosen and how the input updates the state. The same lottery, someone gives you one lottery, they hand you a ticket, and that's enough to know what you're going to input and how state is going to update you.
So for this, if you had like on the right-hand side, like the overall directions for this thing, like what you would have to fill in order to get the machine to move forward is you have 2 versions of like the implementation of the randomness on the 2
On this one?
distributions.
No.
Oh,
the
let's
big one,
well,
the
yeah.
four
There we have
lotteries,
4, yeah.
So you have the 2 lotteries that each get like their random, like universal random thing that
Get
like
their ticket,
produces
yeah.
this thing.
Mhm.
And then you have a direction that is an A,
Yeah.
which is like the agent behavior given that it is the first random process is produced like a B as an output.
Well, yeah. I think so. So given a state, we get an output,
Right.
and for every input, we get a new state. That's what it would say on the top line.
Okay.
The next one is that we non-deterministically choose our output,
Yep.
as well as our way of taking inputs to new states.
Right.
In the
It
third
influences
one,
both.
we get an output that is deterministic, but given an input, we get a non-deterministic state update.
So could you say that again?
On the third one, we
Yep.
take a state, we get a deterministic output,
Yep.
but given an input, we get a non-deterministic state,
Yes.
a lottery on states.
Yeah.
And in the
Process.
fourth one,
Yeah.
given a state, we get a non-deterministic output, and then a second coin is, then we, given an input, a second lottery is chosen that non-deterministically picks a new state.
Yeah.
And
Yeah.
the
And we could put a reward in there if we wanted to and
Yeah.
stuff, yeah.
the choice of input based on anything that's after a lottery is non-deterministic by virtue of because the output is non-deterministic, so the input has to be because the input depends on the output.
Yeah. This, you mean on case 2, given a state, you get a lottery,
Yeah.
and for every ticket, you get a B, as well as a way to take A's to new states.
Mm-hmm.
Yeah.
Yeah.
So that non-deterministic choice of ticket here is also influencing how A's turn into states.
Exactly. Yeah. This makes me want to because the B.
Yeah, there's a lot to say, a lot of questions. Safe. Did anyone get this, or were you paying attention to the other
I
thing?
will say goal.
Oh, nice.
Yeah,
Okay.
Goal.
Oh, sweet. Great.
Goals.
Okay, we just scored some goals. Yeah. Did anyone think about this thing?
Easy scoring goals.
What are we supposed to do?
What is one of these? What are they supposed to do? What is one? How do you think about it?
What
Yeah.
does this mean?
What does it mean?
Yeah.
Who can read it out?
Could you write down the definition of list as a
List,
poly-
yeah. List is the polynomial 1 plus y squared.
Oh,
Plus.
that's right.
In other words, it's the sum over all natural numbers of y to that natural number. Yeah.
So for every state.
In other words, it's a free monoid.
Yeah.
That's free will, yes.
Were you saying something? Oh,
Yeah, so for every state, we get an output, and then given any input, we get a list.
yep, we get a natural number.
We get a natural number, and then we have to give also have to give a list of that length to get a new state.
Given a position in that position in that list, like one of the entries in there, we get a state. So it says we have this state, and it goes to some b, as well, and then for any input, you get a list of new states.
Right.
Of the length of.
Yeah, yeah,
that
of that
choice.
list.
Yeah.
Here's a fact. Sy to the s, I mean, you already know this. This is the same thing as s mapping to b, y to the a composed list composed s, coalgebra. So given a state, I get a b, and for every a list of s's. I can parenthesize any way I want because trie is associative. List trie s means a list of s's.
But this is still a polymath. Now,
It's a set map and all set maps are polymaps.
yes.
Yep.
Yeah, but you write it up. Yes.
So for every state, I get an output, and for every input, I get a list of states.
Shouldn't that be sy?
Where?
Because you have nowhere to return to if that's a.
Did you believe before that we used to be able to? We used to write sy to the s to p is the same thing as S to P of S
Yes, in set. Yes.
in set.
Yeah,
But all set maps are polymaps. The map from set to poly is fully faithful. So I'm allowed to call this a polymap too.
right. I know.
And this is try. There's no directions on either side.
Oh,
Yeah.
yeah.
There's no directions on either side, yeah. Yeah.
It's almost like if you have a, I mean, maybe I'm gonna say something as normal, it's very dumb, but the list at the end there, I mean, it's almost like that's a computational effect. You get a list of S's.
We get a list of
If that had
S's.
been maybe, you would have gotten a maybe, if that had been.
You could have a maybe S.
Yeah, exactly.
Yeah,
Like
you can
1
put
plus
anything.
Y
Yeah,
and
you could put anything there.
You'd have
Wha-
like a computational
you could have a
effect
lottery.
added on.
Yeah, I mean, over here,
non-deterministic
there's,
transition.
well, that's this one, right? Lot.
Yeah.
Yeah. Yeah. You can put any monad you want. You can put anything you want. Doesn't even have to be a monad. We haven't even talked about monads yet, but we're
That
about
is
to.
just amazing, David.
I agree.
Goals.
Here's a fact. I don't know if this is interesting. I think it might be interesting. I wasn't planning to talk about it, but P to Q composed are. There's an adjunction that says that this is poly PRQ. But I haven't defined this symbol for you yet. So what is PR? The sum over I in P1 of y to the r composed pi. You might say, why am I talking about this? But I'm talking about it because compose, try, has an adjoint. And it's written like this.
Yeah.
And it has a formula like this. And you can do it. Okay. So what is a map from poly from S to Q of S?
Compose has an compose blank.
Blank composed has an adjoint. Sorry, Q composed blank has an
Compose blank has an adjoint. Okay.
Q composed blank has a left adjoint. Okay, so this is coalgebras, right? This is S and a map to Q of S. These are coalgebras. This is like this sort of thing. But that's in bijection with, to have a coalgebra is the same thing as to have a polymap from SS to Q. So what do you think SS is?
S y to the S.
Well, it's whatever this says it is.
Yeah.
So it's sum over S and S of y to the power S, but S is a
It's a
set.
It's just a constant polynomial.
So it's sy to the S as guessed,
As
learned.
from the first version of the course.
learned from the first version of the course. So what is a map from A? Let's just pick some weird letters because people like to pick weird letters. What are maps from ST to AB? Polymaps. Well, oh, sorry, what's ST? ST is SY to the T, and this one's AY to the B. So a map like this would be a function from S to T and a function from S times B to A. And this is what people call lenses. So these are, like this thing,
Yeah.
when everything inside is just a set, these gives you lenses. Yeah.
Makes it so happy. It's happy.
Yeah. But this formula works for all possible P's and Q's. Like it's a general formula is adjoint to try. And that's why we were, all along, that's why we were allowed to do this. This weird thing where we did SY to the S versus, yeah. Yeah.
I just one question to first.
Say again?
Alden and I were talking, but I want to talk over you, about like what's still about like what is a thing from SY to the S to BY to A try list.
Hmm.
Yeah.
Like could you guys maybe draw a picture?
I don't really understand what's going on.
Oh, what is going on? Yeah. Okay, I'll try.
Yeah, what is that A?
I mean, it was like the non-deterministic thing. People like that.
It just doesn't have the
It doesn't have the probabilities on it. So it's like this branching.
Oh, I know.
What-
So you try it?
Yeah, yeah,
Okay, so S is like you have a set of states,
yeah.
you get an output that prints for
S1, S2, S3. We get this output, you know, smiley, mid, and smiley.
And then for every input, like 0,
Yeah, given 0.
number of arrows out,
Yeah. There's a number of arrows out, all labeled 0.
and then every arrow, that's like the end.
I mean, there's a first one, a second one, a third one. Yeah.
Yeah, and then the map on direction says for every arrow in my list, I need to pick their target. What
Yeah.
state they're
Yeah.
looking
Yeah.
I don't get what?
You get for every command, let's say you're in like sy to the s to smiley, mid, frowny, y to the 0, 1 or something.
Yeah, okay.
Then what's happening is, given a state, you get an output.
You want to try this
And then given an input, you get a list of where to go next. Some kind of non-deterministic branching.
So it's like not, but it has an ordering.
Has an
to
ordering.
non-determinism.
There's an ordered non-determinism.
What is that already?
Like a first choice, second choice, third choice, fourth choice.
Because it's a list.
A list, yeah.
And then to map backwards to sy to the s, you just like pick an index.
Yeah,
in
for
the
every,
list.
and then for any index in that list, you get a new state.
Can you say that again?
Yeah. I mean, I think maybe is better.
Oh, yeah.
It's not landing for the, I don't know what the A is and how the decision is. The A is the input to the
A is the 0, 1.
0, 1. A
Yeah.
is the 0, 1.
I mean, if we didn't have the list here, we would just write like, you know, given 0, go there, given 1, go here, given 0, go here, given 1, also go here, given 0, go here, given 1, go here, or something, right?
Yeah.
But now, when someone says 0, there's actually a first choice, second choice, third choice of where to go.
Oh, okay. That's not a big deal.
Yeah, it's not a big deal.
I'm so confused by this.
It's not a big deal. Yeah.
Oh my god. Okay.
Maybe it's still a big deal for some people, but not for everybody.
If
Yeah.
I want to say like, even among these first choices, second choices, if I want to choose between different lists, then where would I put the lot monad? Like,
I mean, if you put lot, you could put lot instead of list, and now you have a lottery. Yeah.
together, like list, if I put a lot monad in front of the list, like
Yeah.
if I say
Lot
Y
of
to
list.
the A, try lot, try list,
Yeah.
what would that be?
It would be a lottery on lists, on new states. A lottery. Once someone picks a winning ticket, then all of a sudden, like an ordered list comes out of new states.
So does that A to list of S, you can't take into account the current state, or can you?
No, you can. Yeah.
So it's,
Yeah.
you get to look at the current state when
Yeah.
you.
Given a state, you get an output, and given an input, you get a list of states.
Right. And all later things in that composition kind of remember. the
Oh yeah,
original.
yeah, for sure. Yeah, yeah. The thing that you picked here, everything afterwards depends on it, and then the thing that you picked here, everything after that depends on that. So yeah, they keep depending.
It's very, like, you want to, when you're mapping into a composition, you really are always expanding into new lambdas and like.
Yeah. Yep.
However many your composition
Yep.
has.
So, David, what determines the length of that list?
The input. Given an input, you get a number, which is the length.
So you have a list for a 0 and you have a list for 1.
Yeah. Given a state
Yeah.
This example, yeah.
and either 0 or 1, you get a length of list, and for every entry in that length,
Set of-
you get a new state.
Right,
it's
but
like-
For every
okay.
entry, you get a new state. Okay.
Yeah.
So it's
You get a list of states.
So if A is 0, 1, that doesn't mean you have lists of length either 0 or 1.
No, no, no. A was just a set.
Yeah, exactly. And so what determines which list you're going to get, or you?
This function.
Yeah, okay.
Phi determines how a
Sure.
state gives you an output and how an input gives you an ordered list of states.
So there's some rule that we're
Phi
not
is the rule.
specifying.
Yeah, phi is the rule.
Right. So we
You
just, like,
you choosing phi is you choosing the rule. Yep,
Right.
yep.
So we just define like how long those lists will be
Yeah.
based on our current situation.
Yeah.
Yeah. Okay. So
I
it's
mean,
like-
probably a more interesting, I mean, not interesting, but like a simpler case would be like by to the a composed y plus 1, the maybe monad.
So that would be.
That, given us, yeah.
Go ahead.
You want to say it?
So given a state S, and
You
you
get-
get an output B, and given an input A, you get either a new state or nothing.
Or you stop.
Or you stop.
Or you stop, yep.
Yeah.
Yep. Given a state, you get an output. Given an input, you either get a new state or you stop.
So
Yeah.
like for that first one, it could be that like you get a B, and now you say like your A input would be like how much computational resources do I have to dedicate
Sure.
to like the
You could
next
do that,
branch of
sure.
what
Yeah,
this is
yeah.
gonna do.
That's interesting. So if A was the natural numbers, you could just use it to get your
I have
input
10
there.
nodes available, give
I
me
have
the next
10 I have
things.
10 resources available. Yeah.
This is
That could be
cool.
you could project that out of the A, yeah.
Say that again?
Suppose A was, yeah, so Max said suppose A, this is my interpretation, was A times was natural numbers times A prime. It's some input, but it's also some knowledge of how much computation I have right now available to me.
Mm-hmm.
Then I could feed that answer in to pick the natural number of the length of the list.
The length of the list from which the next possible state can be selected.
Yeah, yeah. So you could say my branching factor right now is 6. Okay.
So you're selecting a
That's
state
pretty
from the
cool.
list.
You're selecting a what?
You're selecting a state from the list rather than doing
Well, no one's actually coming along and selecting that state, really, right? It's just a list of possible next states that, like, your, what are they called? Those, branching universe or whatever,
it's
right?
like a tree kind of thing.
Yeah, it'll be a tree.
Okay.
Yeah.
I mean, this type checking means that when you give an input, you will have a list of states to
Yeah.
select from
Yeah.
when you give an A.
Yeah.
And we like
Okay.
potentially tensor it with some sort of state selecting system that would make it actually select states.
Sure. Yeah.
Feels
Yeah.
like
If somebody came along, if you had a map from, if somebody had a map, if you had like a ty to the t to this thing, then can we do it? Yeah, we can do it. Okay. So suppose you had something that came along and for any state and any list, picked an element of that list. Oh, shoot. This thing is 0. List y is 0.
Oh.
Because the empty list has no way to select. So probably what they meant is for any non-empty list,
How do you define a non-empty list?
list y.
Y plus y squared.
Yeah, y times list.
Oh, yeah.
Okay, so I'll write y list. Y times list to y. Okay. So this says for any state and any non-empty list, pick an element of it. Pick an entry in there. So you have some machine that's just going along. Somebody gives it a non-empty list. It picks a state and picks an element of it. You keep giving it lists,
Yeah.
and it keeps updating and giving you entries in those lists and updating. So it's like, okay, what list do you want me to pick from? You say this one. It's like, okay, that one, and then it updates. So that's a machine. And then somebody else has a machine that was running what we had before. Except they were also careful to get non-empty lists. Otherwise, we would not be able to do this selection. Maybe we can do it, but I don't know how off the top of my head. So I don't know what would happen if we had empty possibilities over there.
Have some extra machinery that makes the system halt if you
Yeah, something.
What happens to y plus 1?
Where's y plus 1?
You can go grab
Oh, I could use y plus 1 this whole time. Oh, okay. Yeah. So, I could. Thank you, Sophie. List y plus 1 would have probably saved me instead of y. Yeah.
Oh, okay. Yeah.
Okay. Should I just do that?
Yeah.
I should do that. Yeah. Okay. Okay. So somebody. This is a machine that walks through lists and is allowed to not do anything. It's allowed to terminate, or it's allowed to give you an entry in those lists. So you've got a machine like that. You hand it a list, it'll either stop, or it'll hand you back an element in that list. And you've got a machine like on the other board that takes a state, gives out a B for any input, gives you a list of new states. Well, somebody's picking from lists and somebody's giving lists, so we would really like to be able to just like get a machine that actually deterministically outputs now from these two. Do you know how to do it?
We can do eval.
Okay. I want a machine. What are the states of my machine? Yeah, let's tensor. So we get STY to the ST to BY to the A. Well, let's do it in order. Oh, I did. Okay, I guess I'm tensoring the other way. BY to the A, compose list, tensor, list, composed Y plus 1. Oh, I hope this works.
We need duality.
We do need duality. I don't know what happens, but something good will happen. Okay, so what do we get? The right thing will happen. Someone will take care of us. Okay. Thanks, Sophie. Okay, what do we do?
I want to replace, well, I want to make an isomorphism, and I want to replace list y plus 1
Yeah.
with y try list y plus 1.
Okay, and now you want to use duality? Okay, duoid. And what do you get?
Y to the A, tensor y, but that's important. Try,
Can we have the tensor one?
list, tensor, list y plus 1.
Okay,
And then Max said he's
and then Max said eval,
yeah.
and we get by to the A, try y plus 1. So this machine takes a state of this guy and a state of this guy, and for any B, prints out a B. For any A, either halts because that weird T guy just halted you for some reason. Maybe you gave him an empty list, or maybe he just halted you. But if you're not halted, then you come back and you get a new state. Because somebody's giving lists and somebody's choosing from lists.
Who's giving this?
S is giving out lists. S is giving Bs, and for every a list of new states. T is taking any list and either halting or giving a point in that list, an entry in that list. And together, they work deterministically to maybe update state. Yeah.
The machine doesn't look very
I'm glad we finally have the technology to do cool things. Yeah.
That's pretty cool.
Yeah.
Sorry, would you mind saying, sorry,
Yeah, it's just in the fee does know also how to pick a new state from the list that A gives, right?
The fee does know, whose fee?
The first one, like
Fee,
way on
fee.
the left. No,
Say again?
No, way more to the
It's not
on the
this?
other side. Yes, that one.
It is this, right?
True. Sorry.
Yeah.
So that one knows how to give a new state based on the list that A gives, or no?
Each entry in the list gets a new state. Yep.
Each entry in the list gets a new state.
Yep.
And yeah, okay.
Every state gets an output, and for every a list full of states.
but does it go to those states?
Yeah.
So it
Each point,
transitions-
yeah.
So, okay, but it transitions to the first, oh, it branches.
Oh, it branches.
Branches.
Yeah, it branches.
Yeah, if you were running
It's
this,
a
if
yeah,
you ran this several times, you would just get
a branching list.
branching list.
But luckily, if you have this thing selecting from lists, you can pare them back down.
I'm sorry, could you explain once again how that works, David, about the co-production or sort of?
How these two work together?
Yeah,
Well, it's this map.
yeah.
And so are you wanting to trace through the map or talk like,
Okay, so.
so this, do you want me to tell you like intuitively why these two together would,
Well, okay, so I guess maybe I'll just make a high-level comment, and you could tell me
Yeah.
if it's on track. So the second one there produces a list. So for a given state, it outputs a B, it takes an A as input, and it produces a list of states.
Yep.
And then the upper one there takes
Starts in the state.
Oh, yeah, it has a state. That's the T component,
Yep.
kind of the state. And it needs a list, and it somehow uses the lists from that second one we just
Well,
produced.
that's not this guy's job.
Okay. Good, so I'm
That's
trying
this stuff.
Okay.
This guy, all it does,
Okay.
you have two boxes working together,
sure,
right? The
sure.
T box and the S
Yep,
box.
Yep.
And they're kind of hanging out in some way.
Sure.
And this is how they're hanging out together. They're hanging out using duodality and eval. Very, very standard stuff.
Right.
So whatever the way these are interacting is like very polynomially approved. Like it's not magic. I mean, it's not chosen. Phi and psi are chosen.
Yeah.
This rest of the stuff is very much.
Okay,
yeah.
so if we talk about psi in isolation,
Yep.
it has a state T,
Yep.
and it maps to a position of that exponential object.
Yep.
And positions of that are wiring diagrams from list to y+1.
Yep. I wouldn't say wiring, but yeah, interaction patterns or polynomial maps.
Polynomial
list
map,
to y+1.
some particular polynomial map.
Yeah.
So T, for a given T, we map to some particular polynomial map from list to y+1.
Yeah.
Yeah. And having done that, we then have backwards map the phi sharp or the psi sharp sub I. That for that given T, it takes all the data flowing on the wires of that. Well, if that were a wiring diagram, it would be all the data flowing on the wires of.
Well, all the
chosen
data.
wiring
Okay,
diagram.
sorry. So what are the it sounds like you're interested in the directions of this.
Yeah.
A direction of this
Yeah.
is written here in an ugly way. But here's what it says. A direction of this is a natural number.
Yes.
So it's like, which list did you give me? So this thing, okay, given T, you get a way to take any length list and
Yes.
pick from it, or fail to do so,
Yes.
right?
Yes. Any length list.
Given any length list,
Yeah.
this machine can pick from it,
Okay, so that closure will handle lists of any length.
of any length, and it'll either pick from it or like fail to do so.
Yep. Yep.
A direction says, well, what list did you pick, by the way?
Yeah.
If I
Yeah.
failed, then there are no directions.
Exactly.
But if I picked from it, I will update my T.
Yes.
So this machine either takes any list and either
Yeah.
picks from it and updates,
Yeah.
or fails and stops forever.
Yep.
But when we do the tensor on the bottom and run through all of this stuff, am I interpreting this correctly that it will actually now, because of the compatibility of everything, pick at the end of it also update S in the appropriate way that phi had
Yeah,
given the
definitely.
list choice?
Yeah.
So the picking that happens in psi is
The pick-
compatible with.
No, the picking that happens inside is not just compatible, but is the thing that chooses from this list.
Yeah, but then that feeds back into S. Because
And that feeds back into S.
Oh wow, that's.
Yeah, this does all that wiring for you.
Yeah.
Yeah. All that wiring is boilerplate. It's
Yeah.
just eval and duoid. Yeah.
It is the thing that you do.
Say that again.
What Max was saying is like, remember how this one picked for any input A picked a list?
But
And-
we weren't happy because it was a list.
It was a
We
list,
choose something
and we weren't happy because we needed to choose something from the list. Well, T is choosing from lists.
Yeah.
And you want to know that like the thing it's choosing is the thing that's up, is the way that we're picking a new state. And the point is that this boilerplate, where all we're using is like, oh, let's try with Y. That's a freebie. Oh, let's use duoid. That's in your code base. That's like a 3-line thing in your code base. Let's use eval. That's a 5-line thing in your, whatever length, right? All that does is it takes these two things and it actually does all that trading and all that, all that stuff has now become boilerplate. All this like handing things where they need to go and crisscrossing all this stuff.
Right,
Yeah.
Oh, because if we,
A lot of it's taking place in the eval.
It's a bit like Legos, you have the right blocks, and you can snap them together to make it bigger.
Yeah, you can snap things together in pretty amazing ways. Like I've been like blown away
that's
by.
a pretty big goal.
Yeah, yeah, it's like yeah. I'm glad you see it. Yeah, it's pretty like it just does stuff that you want to do. It's like yeah, of course you want to do that. It's duality. Of course. Oh, it's eval. Yeah, I knew you'd want that. It's just that the things that you tend to want are the things that tend to be given. So that's yeah.
If you look
Gratifying.
at the output of like the ultimate output of y plus 1,
Yeah.
like the last polynomial, it's either
It either failed or
nothing
didn't.
or
Yeah.
a single thing, and that just goes
And
back
that
to
yeah, it either, this y plus 1 either fail or a single thing, and the single thing is a thing selected by t. Yeah. Sorry, Eric.
Well,
Yeah.
and I was actually just going to ask about that. So the reason why we're mapping list to y plus 1, the y, like 1y to the 1 means we're selecting one thing out or one index out of that list, and plus 1 is or we can fail.
Or we can fail. Yeah.
Okay, cool. Yes,
Yeah.
So it's awesome. It's
big goal.
Yeah. Cool.
like thinking about the last thing at the end of a composition as like the ultimate like the thing that will determine how you move to the next state.
Yeah. I mean, but to be honest, this did too. That A also determined it. Everybody along the way determines it.
Yeah.
Yeah. But this one does have access to the previous one. So this one's like the final decider.
Yeah.
Yeah.
It makes me want to think of. It's almost as if this was a map from STY to the ST to y plus 1.
No.
Except that it's just almost like that in the
I
sense
see.
that like
Okay.
the ultimate step is always going to be direction. The ultimate input is going to be a direction in
Yeah.
y plus 1.
Okay.
But I know that ultimate input that comes with a lot of caveats. Like
Yeah,
you
yeah,
have to choose
yeah.
that for y to the n.
The
Yeah.
toolkit metaphor, the thing that I'm getting here is that I've always wanted this notion that you should have constructs, a toolkit that are the sort of natural ways to building up to concepts that you want to implement.
Yes.
So, programming languages seem to have too much freedom in them.
It has too much. Yeah. Programming languages have a
And you
ton of
want
freedom.
the constraints.
We don't
You
want. Yeah.
you
We want
that-
that. We want to factor it. Duality.
Yes,
Eval.
yes.
Tensor with y. That's what you're allowed. You know, just and anything where you're not seeing these types of words, somebody's doing something. That's where the interesting stuff is. If you were going to go like check, is there a back door in this code? It would not be in the duoid or the eval.
In the distant past,
Yeah.
I used to use go-to statements in my
Yeah.
Fortran.
Yeah.
And then they gave me block if statements.
Yeah.
Okay, that makes it much better.
Yeah.
Now we're really light years ahead. Now we're
Yeah.
doing like
This is just
really
plumbing.
good.
It's just so much plumbing. This handles crazy amounts of plumbing. Yeah.
It feels like you're creating syntax almost
Yes.
just from the primitives.
Yeah.
It's like,
Just from the
yes,
primitives. Yeah.
You can
Yeah.
state something, a machine that does insert incredibly complicated natural language thing here, and it's just a bunch of
Yeah.
canonical.
But the person saying all that natural language that's incredibly complicated, they know in their mind, no, guys, this is simple, I swear. And then now you're like, see, it was simple. Yeah. Yeah. You don't want it to be the case that you have this feeling like, no, I swear this is simple, but it takes you an hour to explain it. That's a terrible feeling. And that's what this obviates. Yeah.
So can you help me understand, if that were instead of y plus 1, if that were y squared plus 1,
Yeah.
would it be picking two things
Yeah.
from the
It'd be
list?
picking two things from the list. Yeah.
And
Or failing. Yeah.
help me unpack that.
That's a branch of two.
A two branching. Yeah.
Yes.
And then nobody's picking which one. Now it's non-deterministically branching. So maybe we make a UY to the U that does a picks out of two.
Okay, but
Yeah.
I'm still trying to grok here. So you've got this closure or this
monoidal
this,
closure? Yeah.
exponential object,
Yeah, it's a monoidal closure.
and the positions
Yeah.
are these sort of polymap. Position is a polymap from list to y plus 1.
Yep.
And the directions of it, which will be influencing what you have to go back from
Yep.
over to the left side, the directions of it are,
A choice of position here,
yes,
and then that'll open up. That'll give you position in Q
Yeah.
because we had this phi,
yeah,
and that therefore opens up some directions in Q.
yes,
So it's a position in P and a direction in Q.
right, so.
So it's a position in P, a length of list,
Yep,
and then
yeah,
well either
Yep.
we failed or we didn't.
Yep.
If we failed,
Yep.
there are no directions.
Yep.
And there's nothing to go back from.
yeah,
And if we didn't fail,
yeah,
then there's one direction.
right, okay, so So all of this is contextualized in a broader context where we also came from some position in T. But this is like an inner.
Yeah, we have the
Construct.
position of T,
Yep.
and that's determining this phi.
Exactly.
Yeah.
Exactly.
It's
Yeah.
also determining how a success
Yeah.
will, you
Yep.
know, a choice of
Yep.
list and a success will update the T.
Yep. Yep.
Yeah.
Okay.
Yeah.
Thank you, David. Thank you.
Yeah.
Thank you, Dave Gold.
Cool. Okay, I just want to do number 3. But does anyone want to see these?
I'm just curious for the tensoring of the first one, would we do what we did there and do ST or TS?
Oh, ST and TS are commutative.
Yeah.
Doesn't matter to me.
Okay.
Yeah.
I just wanted to make sure.
Yeah.
It's the same thing, just
It's yeah. There's an isomorphism between sy to the t tensor ty to. There's an isomorphism between sy to the s tensor ty to the t and ty to the t tensor sy to the s. Yeah. Okay. Yeah. So in this one that Solomon came up with, given a state, you get a b, and given any a, you get a b prime, and then given an a prime, you get a state. So it's like a 2-step machine. For whatever reason, this machine outputs strategies that give a b, wait for you to give it back an a, and automatically know what b prime they're going to give.
You get kind of an intermediate calculation.
You get some kind of intermediate calculation, and then given an a prime, you get the state. So these are just kind of weird things you can do. But I wanted to do this one because I think people are really trying to understand py,
Yeah.
and not just the maps from p to y or maps from p to y plus 1, but also the directions of this polynomial. This whole thing's a polynomial, and so is this. Okay, so when in Joachim Koch's talk this morning, he'd like to draw polynomials as bundles, and it is convenient to do that sometimes for us also. So if this is p, it would be y to the 4th plus y cubed plus y cubed plus y squared. And these 4 dots go here, these 3 dots go here, these 3 dots go here, these 2 dots go there. Okay, so that's how he likes to draw them, and 99% of all mathematicians in the polynomial world like to draw it that way, and I just like to draw it this way. Okay, so I'm the odd one out here. So for A and for B, I want to solve this problem. So can someone tell me how to draw a element of py, a position? Does anyone know what a position in this is? It's a map from p to y, which sometimes in the past I've called situations. So if you're a p, you output positions, you do stuff with your body and make noises and stuff like that, and then you receive directions from the universe, from the environment, based on what you're doing. If your eyes are closed, you get a different sort of data type than if your eyes are open. A situation says there's a situation around you, and I don't care what you do, whatever you do, wherever you look, there's something waiting for you and giving you something back.
Depending upon your position.
Depending on your position, no matter how you orient your body or look through the space,
Sort of
something is sitting there waiting for you, and that's a situation.
It's the aggregate of all the inputs.
It's all possible inputs, no matter where you might be looking. So what it is, it's also called a global section. We wrote this as gamma. So for every position, it's a choice of direction. A map from p to y takes every position and gives you a direction there. So how would you draw it? Yeah, it's a global section. You pick,
It's a snake
yeah. Yeah. Okay, what's a direction there?
there. A direction in that.
Yeah,
Next
in
one.
this is a position,
Yeah.
so it has directions. What are they?
All the things flowing on the wires.
Well, there are no wires here. In the formula, what does it say the directions are? Sorry, what are the directions? How many directions are
Choose
there?
a position in P,
Yeah, choose the position of P
and then choose a direction of Y, which is the right one.
Yeah, it says choose a position of P, okay, it's one of these 4, and then pick a direction of Y. Well, there's always just one, so there's exactly 4 directions. This one, this one, this one, and this one. Maybe it means this one, this one, this one, and this one. There happen to be exactly as many. So we don't know which one right now, which one Poly was actually thinking of when it told us this. But this, yeah, this direction here went back to a direction of P, so it could have been these four also. We're not sure what Poly really meant, whether Poly meant a direction is one of these, or that a direction is one of these. How you should represent it, because they're like, we have a feeling like it wouldn't be rude and just pick some 4 for no reason. It's got to be either this 4 or this 4. But yeah, go ahead.
Can you go a little bit slower? So I understand that the positions of the bracket are a section.
Yeah, a position of this bracket is a global section.
Yeah, and a direction.
A direction, okay, what is PQ, HOM PQ? Position is a map from P to Q. A direction is a choice of position here and direction there. Position here, direction there. Well, if Q was just Y, then it has exactly one direction. So it's a position here, done.
Okay.
And so we pick a position and we're done.
Okay. So it kind of flips things around. Like it's the positions there are the positions in the bracket are directions of P, and the directions of the bracket are positions of P?
Yeah. Well, the direction of the bracket, so it's like, what are the problems? The problem is to pick a map from P to Q.
Yeah.
And then what's given back, what's the direction? Or those are the positions. The position is a map from P to Q. A direction is a position of P and a direction of Q. I don't know why. I mean, it made sense. It's to fill in all the necessary inputs.
Yeah.
It made sense when we were looking at these sorts of things, because it's all the stuff that you would need that's flowing on the wires, right? It gave you exactly, in those cases, it gave you exactly what you wished it would give you. But now that we're looking at the abstract, it's like,
Sorry.
I don't know why that's good.
Could I clarify something there? Because you said the directions
Yeah.
are for each position of P.
No, a choice of
or
position
a
of,
choice of position of P, I'm sorry.
a choice of position
Choice
of P.
And for that position of P,
Now we have a position of Q,
now we have a position of Q.
and so its directions are now available.
Right.
Pick one.
But we're not choosing all of them?
One direction here
Yeah.
is one position in P and one direction there.
One direction at that position.
One direction at Q's position.
So isn't that, maybe I'm misreading it, but. from-
Sorry, I'll try it again.
Yeah.
To address a position is a map from P to Q.
Yes,
A direction is a choice of position in P,
yes,
Yeah.
which therefore gives us a position in Q,
yes.
Yeah.
and it's a direction in Q there.
Okay, but what is it?
Yeah.
Why isn't it all directions at that?
Well, the union will be all of them, like they're all in there, but I'm just choosing one.
So how is that?
Okay, let's do a different one.
So okay.
What is a y to the b
Yeah,
to c y to the d?
right,
It's a function from a to c
yeah,
and from a times d to
yeah,
b. So phi 1, phi
Yeah.
sharp,
yeah, that's the polymap.
y to the what?
Well, choose a position in.
Choose a
P.
position in P.
So it's either, it's A1 or A2 or A3,
It's
whatever.
A
plus
colon
or
A.
minus. Yeah, you have different A's. Yeah.
Of
Of Q, which is D.
Q bracket
Okay, yeah, Q bracket, okay.
whatever position I was at. So it's a direction of Q. So it's D.
D, okay,
In other words, this is sum over all maps from A y to the B to C y to the D of A y to the AD. A times D. Now, would you say that's all of the directions of D? Yeah, they're all the positions of A and all the directions of D are in here.
are possible,
Are possible.
but
A
only
given
one of them
direction-
gets selected.
A given direction is a given A, given D.
Okay.
Yeah.
Cool.
Cool. Okay, so now I want a position of this thing. What is a position of this thing? Is this too much? Are we going too fast? Okay. A position of this is for every position of P, a position of y plus 1.
Yeah.
And if I chose this one, a direction back there.
Yeah.
And if I chose this one, we're good.
Right.
Okay, so it's like a local section. Instead of a global section, it's just some of them have to get picked. So maybe it's like these two and this one, where this one got sent to 1. And all the rest of them got sent to y. Like each one of them was sent either to y or 1, and the one that failed out, that hit nothing, did not get to pick a section going back, a direction going back. Okay, what are the directions at this local section?
For each position,
A direction is a choice of position. Okay, it's one of these 4.
and then you apply the P map. So you know if it's y, yeah.
We know if it failed or picked. Yep.
Right. And then it's just that.
And then we add up. We say we're going to put it in
Yeah.
if it hit this one. We'll pick 1 if it went here, and none if it went here.
Right.
So what are the
That's our
directions?
Yeah.
What are the directions? There are 3. Yeah. And now we realize that it probably meant to pick one of those. So the positions are these, and the directions are choices in there. I don't know. That's how I see it, at least. A position is a way of choosing a local section. So it's got some of them and not other ones. And a direction is any of the ones that it picked.
The direction is the local section.
Yeah. No. A position is a local section.
Okay.
A direction is one of the dots in it.
And
Should we do another one?
Yeah,
Do you like this?
please.
Okay. So, okay. Pick. Here's a polynomial. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2. So I have y to the 6th. No, y to the 5th plus 2y to the 4th plus 2y squared plus y. Find a map from that. That's P. Just everyone write down a position in that polynomial, and then pick one direction and write that down. Maybe we should like do a Sophie style. Everybody do it on the board. Maybe that'd be fun. What? So I'm just going to make space for like a bunch of them, I guess. Or I'll do it here, I think. No?
Oh. Can I?
All right. 13. Okay. So try on your paper to get one as fast as you can, if possible, and we'll start in on it as soon as I draw a few. Okay. So P was y to the 5th plus 2y to the 4th plus 2y squared plus y. This is hard?
Who knows? Should I raise this cord and draw some? Is that what you
Oh, I was just going to do them over here.
Okay.
It's a bunch of people picking them. Okay. Okay, we need a bunch of people to pick maps. Huh? Yeah. Okay. Is that what I picked? 5, 4, 4. Yeah. Okay. Does anybody have one?
I mean, I think you can have one where you just don't pick anything.
Okay, so we got one. And you have to pick a direction of yours.
Do I, or is it just?
I said to pick a position and a direction.
Well,
Okay. Pick a position and a direction.
just circle one anywhere. I mean, that's also a direction.
Okay.
Yeah,
Okay. So what did Thomas choose? For this one, did he go to y squared, y, or 1? When Thomas chose this, where did he send this? To y squared, y, or 1? 1. For the first one, where did he go? For the second one, where did he go? Y. Okay, and then what direction did he pick? I don't know, the first one or something. 1, 1, 1, 1. Yeah, 1, 1, 1. Okay. If you didn't get it, then you have to wait for somebody else to do theirs.
Okay.
Okay. If you don't get it on the last one, then I'll help. Okay, so does somebody else have one? What? You ready? Okay.
I want to choose two.
In the first one?
Yeah. Any two things.
Okay.
And then nothing in the next.
Okay.
Two things in the next.
Uh-huh.
And then one thing in the next. And we leave the rest.
Okay. And what direction do you choose?
So I choose that thing one, like you circle twice the same things for one.
Okay, you just choose it.
Yeah.
Do you need any more information?
I can't choose anything else, so that's
Well, the problem is you have to tell me whether you picked the smaller circle or the bigger
Oh,
circle.
right.
Okay, so I guess you picked do you pick the left circle or the right circle? You picked the left circle?
Yeah.
Okay. Okay.
Okay. And then next I don't choose anything.
Well, you're done, right? That's it, yeah. So for Priya's, where did she send y to the fifth? To y squared. And then, oh, I'm sorry. What? Wait, what did I do?
Yeah. Other local sections.
What? What did I do? Oh, no, I'm good. I'm good. Yeah. Whew. Okay, yeah. Yeah, and you picked, the direction you picked was this position and that direction, one of those two directions. Yeah, okay, cool. Okay. Anybody else want to do one? Is anyone else confused? Or on the border of confused? You're on the border of
Well,
confused.
again, with Thomas's, you went through each of the positions.
Oh, yeah, so she took y to the fifth to y squared,
Right.
this one to what? 1. This one to
Y squared.
y squared. First one to this one to
First one of that one to y,
second one.
to y, to 1, and then that one to 1.
Yep.
So at each position, we can choose either 2, 1, or 0 of them.
For each, yeah, a polynomial map for each position here picks a position here.
Yeah.
And then for each direction here picks a direction there. So it picks whether you want to have 2, 1, or none.
Yeah.
And then if you chose, whichever one you chose, it's that many selections of direction. That many choices of direction.
Sorry, I still kind of confused with Prius. The first column, y is not, y is y2. Why it is mapped from y5 to y2?
She chose this. She chose 4, 4.
Oh, okay, those pair of
Yeah, 2 different elements of 1 through 5. Yeah. Anyone want to do another one? Yeah.
Oh, I don't want to do it.
Yeah.
You want one done?
Yes.
Okay. Can someone who just got it do one? Peter?
I don't know, yeah, I think I can do it, but give me a minute.
Okay.
I think I get the position side of it. I'm kind of confused about the directions.
A position, a direction of
Like
Of
how
this
you-
thing?
Yeah, how you,
A direction is a choice of position here.
yeah.
So which one we're in, and then a choice of direction here. So if you were in this one,
Yeah.
and you picked 2,
Yeah.
you tell me which one is your direction.
Oh, between the 2 options.
Yeah.
Okay.
Both people so far have done like kind of weird things.
Yeah.
Thomas wanted to pick all ones, but I forced him to pick a direction because I said so in the beginning. So then he updated and just picked a single.
So let me try.
So-
Okay, here we go, Peter.
I'm gonna try one. So
All right.
the first position, I wanna pick 2.
Okay. Which, these 2? Yeah, you do. Okay, which 2?
No, that's fine.
Okay.
And I wanna do that, I'm gonna map all the positions of P to y squared. which
Okay.
means I'm gonna pick 2 for each one. And you can, it's up to you. Yeah, there you go. Yeah.
Okay.
Now,
I need a direction of this thing.
now I have to pick of the 2 positions.
You need to pick as a position in P.
Yeah, so at that position P, I've got
Which
to
one?
pick
Which position P?
the first position.
You're going to do the first one again? All right.
Yeah, and I got to pick a
A
direction.
Yep.
Which is going to be one of those. Yeah,
Okay.
and similarly for the rest.
No, you're done. That's a direction.
Well, I mean, okay.
No, that's it. Yeah.
That's right, that's right.
I didn't ask you to pick more than one direction, just a direction.
Just a direction,
Yeah.
okay.
The specific
Pick a
instance
posi-
of a
and a
position
direction.
we chose.
A position and a
choose
direction. Yep.
That's why there is a sigma there, not a pi.
That's a sigma, not a pi. Yeah.
Yeah, okay.
Yeah.
I'll do one.
Okay.
So I'm going to choose everything's going to map to y.
Okay.
And so I'm going to choose the top one of every one. Yeah.
Okay, and then what's
And
your?
then I'll do the last one. I'm going to pick the one that's
Yeah, cool.
as the direction.
Okay, great.
Yeah.
Okay.
That clarifies a lot.
Oh, I'm glad. Okay, great. This clarifies how polynomial maps work. Those are exactly these sorts of weird pictures, and how this internal HOM works.
But the internal HOM is all the possible ways in which you could,
These are 4 different positions in this thing,
yeah.
and for each one we chose one direction.
Each one of them is,
I asked you to choose a position and a direction there.
each one of those is a different position in the.
This is a position, the red thing here is a position, the red thing here is a position, the red thing here is one position, and the red thing here is one position. For each of these constitute 4 positions if we just look at the red part. For each of them, I also indicate a direction at that position. That's a direction, that's a direction, that's a direction, and that's a direction.
For the entire
Position.
Why is it only
circular chunk. Like
A position
all the red
is- a
circle
position
my
is-
position, so it's for the entire
Position.
all the red- yeah.
Can someone else do it?
so why do we only pick one direction?
Because I asked you for one direction. But
Oh,
do you mean
okay.
why is the direction what I said? Because, yeah,
So
because
for each of
PQ
these-
is sum over, for every position in P, pick a position in Q, and for every direction there, pick a direction back home.
So
So this is the red part. Y to the sum. Now pick an actual position in P,
Yeah.
one of these guys,
Yeah.
and then pick a direction in Q, one of these guys, at
Yeah.
the position that you were sent to.
and we only pick one of the directions.
Yeah, to pick an element of a sigma, you pick one of these and one of these.
So
You have a-
we get a polymap from P to Q, and for that polymap we pick any of its positions, and then
So we have a position, a polymorph from P to Q, that's a
Yeah.
position. Now we're going to look for a direction there, which is in blue.
okay.
Okay, and then now you started saying, what were you going to say? You pick
direction back is one of the positions of P.
Yep, one of these, 6 things.
Yeah. And then
You pick
for that position, you pick what is that last? The Q of
Q, a direction in Q over the position
Which is a
you had been sent to.
which is a set, but you pick one of it.
Yeah.
Pick just
This,
like
to pick an element of
Yeah.
sigma A and A, BA,
yeah.
to choose an element of this, choose A in A and B in BA. Just one.
So it's like for every position of P,
Yeah.
we pick one direction back.
No.
But we're summing over this.
Pick a.
functions.
To choose one of these, choose one, not for all. Not for all. It's not a pie.
Yeah, but I mean, we have the option to choose.
You have the option, but you're just choosing one.
Yeah, but in the same way as we pick a direction, but each direction does have a mapping backwards, like in a normal.
Yeah.
I think, David, maybe the confusion is the subscript of the sigma in the frontmost sigma is a function.
Yeah. It's a polynomial map. It's a way to go from positions of P to positions of Q, and then to take these things and label in red.
Yeah.
This thing is in red here.
But I guess the point is that because you're choosing a map, phi, then you have to choose you have to define where all the positions go.
You mean in phi?
You have to assign a Q position to each position of P.
Yeah.
And that's
Yeah.
why you have
Every
all
one
the
of these
different-
chose whether to have 2, 1, or none.
Pick an element of every fiber.
No, pick either 2, 1, or none in every fiber.
You're
Yeah.
right.
Yep. Yep.
That's a really cool generalization of local sections.
Yeah. Yeah.
It like gives you more bookkeeping of like keeping track.
You're good?
I'm still gone, but this is one I'm gonna have to convince myself of.
Okay, yeah.
I'm okay for now.
Okay. Yeah. So a map SY to the S to PQ, for example, will take any state and give us a way to move to like turn P's into Q's and turn Q directions back into P directions. Yeah, I don't know. I'm not sure this is useful. And then given that state and that position in P and a direction in Q, give back a state. Yeah. I don't know. Yeah. Yeah.
Okay, one last thing. Can we do the same translation for list y plus 1? Like,
List Y plus 1?
yeah. Just I want to write it.
Well, I mean, I don't think we can do it. We can do some, I guess. Okay. So what is a map from list to Y plus 1? So it'll be right. So we can't actually do it because we never stop. But we can. Okay. So for each of these, you tell me, do you want to send this to Y or 1?
1.
Good. Otherwise, you'd be in trouble. This one?
Y.
Okay. This one?
Oh, I have a choice every time.
Yeah, Y or Y plus 1, yeah.
Oh, okay. So I may not send it anywhere. So 1.
Okay.
Send it to 1.
This one?
To Y.
Okay.
I'll choose something there. Okay. Y. I'll go for Y for everything else.
Well, then I have to keep going forever.
Okay, I'll halt it.
Thank you. Okay. And then I need a direction.
Oh, okay. I'll
What's-
go for the 5th one.
Oh, okay. 1, 2, 3, 4, 5. Okay.
Or I could have halted as well.
You could have halted, yeah. No, I asked you for a direction.
Oh, direction, yeah.
Yeah.
Okay.
Okay. Yeah.
If I choose position 3, then there is no direction.
Yeah. You could not have succeeded if you accidentally chose position.
Stop.
Yeah. Yeah. Okay.
Thanks, David.
Sure.
So
14, I think. Yeah.
So I think you emphasized that this same method that you just used is also useful for just reasoning about polymaps more generally outside the exponential object context. Right? Like
Yeah.
we could use it to visualize polymaps.
Visualize polymaps.
In other words,
Yeah, I
here
mean,
we're-
if you want, yeah, you
Yeah.
could, yeah.
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 It's a nice way to visualize what a polymap is doing.
Yeah.
Can I
Yeah.
ask a dumb question about map from P to Q?
Yeah.
If P, so let's suppose P has output. So
P has
let's
output?
see.
You mean P
So
is not
the
0?
different types of. So imagine P is a monomial.
Like AY to the B?
Yeah.
So Joachim by monomial wrote, he meant what we called representable.
Okay.
So
Yeah,
yeah.
right.
But we use monomial in the sense of high school algebra. So,
Right.
okay, just
So
clarifying.
if we had that,
Yep.
and if we were to change A,
Yeah. Change
If-
it. We just put it.
we were to consider a dynamical system.
Oh, you have a dynamical
Well,
system.
So that's Q. Let's suppose that's Q.
Yep.
Yeah. And we were to consider one dynamical system where A is just 0. Another one where A is 0, 1. Another one where A is 0, 2. How would the behavior of that dynamical system be any different?
Are you giving me different Qs?
Yes.
So you're saying, what if Q1 was this, Q2
Yeah.
was
Well,
A2 y
Yeah,
to the
exactly.
B?
yeah.
In the first one, every state would be able to take a P. It's
Yeah.
kind of like we got a P inside of a Q thing. And
Yeah.
every P
Yeah.
output
Yep.
would give us
Yep.
an element of A.
Right.
In this one, every P output would give us an element of A2.
A2.
Yeah.
Okay. Okay, but would that dynamical system actually be performing the output? I mean, it would be like
Oh,
for each S.
let's say I know what to do. I know what to do. Okay.
Okay.
So we have SY to the S to
Yeah.
PQ.
Yep.
This is some machine that's like updating
Updating its wiring diagram.
all these wiring diagrams.
Yes. But is it actually outputting different?
And then somebody gives us T1 y to the T1
Yeah.
mapping to P1. T2 y to the T2. So now they animate all the
Yeah.
they animate all of these
All
for
the
us.
internal dynamical systems.
They animate all the internal dynamical systems.
Yeah.
So we've got this machine. You know, it's got n many boxes inside,
Yep.
and there's stuff flowing, but psi, phi,
Yeah.
is like this machine that's deciding who's wiring to who and how it's leaving and all that sort of stuff.
That's right.
And then each of these guys, P1 through Pn, is animated by phi1 or psi1. In other words,
Yeah.
there's dynamical systems inside of each of these.
That's right.
Then how do we get a dynamical system inside of Q?
Well, yeah. I mean,
We're supposed to be able to, right?
Tensor,
Tensor?
you get
Okay,
a
SY to the
them
S.
together because you have P's, PI's tensor together, so you can tensor together these maps that go
Okay.
from the dynamical systems, to the various PI's, not principal investigators, and then you.
I switched this by mistake. Sorry.
Yeah.
Okay.
Oh,
And then what do you do?
sorry. Oh. Okay. sorry, I'm just trying to figure out where you got that. I was thinking.
I did exactly what you said. You said to tensor them.
Oh, no, sorry, I meant to tensor the subscripted ones.
Well,
Which,
okay.
Which would give.
So I just have to cross out this
That one, yeah.
and this.
Yeah, exactly.
Okay.
Okay, so then we could somehow compose that with this map to Q from P1,
Yeah.
tensor P2, tensor P3.
Yeah. Well, instead of mumbling, let's just tensor all of them together
Okay.
and tensor all the outputs
Oh,
because this is a
eval. Then we do.
then we do eval, yeah.
Eval.
Yeah. So this is
Yeah.
phi tensor psi 1 tensor dot 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 tensor psi n.
Yeah.
And I accidentally switched these. Sorry about that. And then
Yeah.
then eval.
Then we do eval, and then we can get a Q.
Yeah.
Yeah. Okay. Okay, so I'm still trying to figure out if we were to have so this dynamical system
Which in?
going from
This
sy to the s to pq to that
Okay.
exponential object.
Okay, which is also this one.
Yeah.
Yeah.
It's picking wiring diagrams from P to Q, or picking polymaps from P to Q.
Yeah.
Is it also doing the work that P would do in outputting things? Like
P outputting things?
sorry,
No.
Q.
Q
sorry.
outputting things? Q.
If Q outputs
Well,
A1,
once these guys. No, P. If P outputs, then Q can output. P is doing this map phi here
Yeah.
is doing the thing that takes a state to a wiring diagram or an
Yep.
interaction pattern.
Yep.
But that interaction pattern is still waiting for P to output. Once P outputs, gives a position, then Q gets a position.
Okay.
Okay, and that's what this is saying too.
Got it.
These guys are providing ways of getting P1 to put out positions, et
Got it.
cetera.
Okay,
Yeah,
cool.
great,
Cool.
great. Other questions? Okay, so let's move on to monads. Monads are just trimonoids. So like the elders of category theory told us that whenever you have a monoidal structure, you should be interested in monoids and comonoids. So we are interested in what in the world are trimonoids. And those are, if we think of poly as set, arrow, set, then a trimonoid, tri is composed. So this would be set to set. So a trimonoid is y to p and p composed p to p. We'll call this eta and this mu. We often call it E and M, but when it's not symmetric, it's even weirder to, I don't know, I want to call it that. So here we have P, and here we have P, and here we have P, and this whole thing is P tri P, and that's mu.
What's the
Oh my
symbol on the
goodness.
Y, Steve?
Hmm?
What's that character on the Y?
Eta.
What?
Eta.
Oh.
ETA.
That's our old friend.
Monad.
Yeah.
Yeah. So a polynomial monoid, a monoid in a trimonoid, is a monad on set, called a polynomial monad on set.
Funny meeting him here.
Yeah.
Or her. Her here.
Polynomial monad. What is such a thing? Yeah.
So it's the thing that's sort of producing polynomial structure on set.
No. All polynomials are functors from set to set.
Yeah.
The fact that we're thinking about them as functors from set to set right now is just to connect with all those people who think of these as monads.
Yeah.
They are monads on set.
Is there
But
ever-
for us, they're just trimonoids because we don't.
Yeah.
We think about polynomials as data structures most of the time, not as, or I think of them as data structures, not as functors from set to set. But if we want to, they are functors from set to set.
Yeah.
And out of all the monoids, times monoids, tensor monoids, trimonoids, we've looked at those. We've called them alternatives and applicatives and stuff like that. These already had a name for us, and they're called monads. So we'll take that name. these will be called polynomial monads.
But, yeah, so what is called mu here now,
Yeah, instead of
sort
times, yeah,
join
the join, yeah.
is equivalent in the monoidal context, when we
Yeah.
just considered p's, we weren't considering them as monads, we had a different name for that map.
We called this thing star
Yeah, exactly.
and E.
In E,
Yeah,
that is beautiful.
I'm glad you like it. I like it too. Yeah, so for times monoids we call it E and star, and for tensor monoids I called it E and star. But for some reason, I don't know, I don't want to call it E and star right now. I don't know why I don't, I just don't. If that's okay, this will be called eta and mu, which is like the more normal classical way that people might notate these. This was called the unit of the monad. Functional programmers call it return. And this is called the multiplication of the monad. And functional programmers call it join. Okay, so now we just want to give a whole bunch of monads and think about them and think what they do. In general, monads concentrate everything in the world, like any number of p's multiplied, composed together, will be able to turn into one. It's like concentrating down to just one. No matter if you had none or lots, you can always get one. And comonads, which we'll do tomorrow, project out or disperse. So monads try to collect, comonads try to disperse. Comonads take a p and give you as many p's as you want. 0, 1, 2, 3. Okay.
Sorry, can
Yeah.
you just explain the two diagrams?
Which, these two?
Yeah.
Well, do you agree with this?
Yeah.
P is a polynomial functor.
Right.
So if we want to, we're allowed to think of it as a map from set to set. This is wrong.
It's an endofunctor.
Okay, poly is not just all maps set to set, yeah. So it's a functor from set to set. And a map in poly is a natural transformation of functors. The objects of poly are polynomial functors. The morphisms are natural transformations. So if I have a map like this from y to p, then, well, y is the identity functor. So I draw it like that. Or maybe if you want, I draw it like id set.
Okay.
And p composed p is do p, then do p. And a natural transformation from p, then p to p is one, shaped like that.
I see that. Okay.
And so a person who didn't live their entire lives in poly like I do in the last 3 or 4 years would probably think of these as monads, like functors and natural transformations.
Yeah.
Whereas since if you just live in poly all day, then these are just polynomials and maps, and it's another monoid. It's a monoid for just another monoidal structure.
Cool.
Okay. So we don't usually want to write a bunch of sets on the board and arrows as though it's complicated like this when we could just think of it like that and just live inside there. Okay. Tomorrow when we get to comonads, then we'll be able to recover all the stuff Joachim Koch was talking about today with like multi-variable polynomials. But for today, we're just in one polynomials, one variable polynomials. So these are going to be polynomial monads in one variable, and these correspond to certain kinds of operads, very, very nice operads. Okay. So what I want to do is give you a bunch of examples of polynomial monads. Okay. I wrote some down. Okay, suppose, now most people who in like math, if you want to write a monad, for some reason originally they were called triples because they have 3 things in them, a p, an eta, and a mu. And I think it's for that reason that people denoted them with a capital T a lot of times. So I just to be kind of in keeping with that, suppose T and U are monads. Now T is a polynomial. It's not a monad. It's a polynomial carrying a monad structure. So suppose T has an eta and a mu for it, and U has an eta and a mu for it. Is that okay? Okay, then I'll give you a bunch of polynomials, monads. Well, I'm not going to use them at first. So list why, I don't really need this one, but Y is a monad. 1, list is a monad. 2, lot, I don't know why I'm writing is a monad each time, but I guess I've started it. 3, T times U is a monad. T composed my is a monad for M, a monoid in set. I'm almost sure of this one. I just wrote it down this morning because I wanted I'm pretty sure of this one. I wanted the POMDP stuff.
Yep.
Remember with the rewards?
Yep.
So I thought, okay, let me just check that real quick. I haven't.
So,
Yeah.
I have a question.
Let me keep going for a second, and I'll be done in a little. Almost done. T to the P is a monad for any P in poly. 6. CT is a monad for any C a comonad. We haven't gotten to those yet, so you'll just have to. And then 7 MP is, well, that's the free monad. And we'll get to that hopefully we'll get to that today.
And a comonad would be a tricomonoid?
A tricomonoid, yeah. Okay, so I'll take the question, and then we'll try to pick up some of the normal polynomial monads that people know about from these.
Yeah, so you just.
For any C comonad, yeah.
So you
comonad.
for number 4 says
T tri my.
but so monads don't compose.
But T tri my has it. So when you have two monads, T and U, this thing is not typically a monad.
Right.
Unless you have what's called a distributive law. That's like a way to turn U composed T into T composed U. Because then if you had that, then if someone gave you a T composed U composed T composed U, you could turn it into a T composed U composed U and get the T composed U.